So, the topic that I'm going to cover today is at least skeletal aspects of magnetism and matter, which is the chapter right after magnetic effect of current. This chapter predominantly, for school boards, JEE mains. It's not there in JEE advanced syllabus, but JEE mains it's there, and it's an important chapter for school exams and board exams. At least the most important parts of this chapter I will cover, so that you are taken care of in terms of your school exams and board exams. A little bit you might still have to read up, but I'll try and do as much as is at least required. That means magnetism associated with the earth. Magnetism associated with the earth. Earth creates its own magnetic field. And it can be sensed in various ways. Because if there is a magnetic field, then, there are ways to sense its presence, establish that there is a magnetic field due to the earth. The cause of this magnetic field, exactly not known. Exactly not known. But it is believed, largely believed, that it could be there is molten iron inside the core of the earth. Molten iron inside the core of the earth. And that iron is ionized, therefore it's charged. So when the earth spins, there is an equivalent current associated with that molten iron charge. It's ionized, therefore it has charge. And that creates a magnetic field. We know that when a charge circulates, it creates a magnetic moment and therefore a magnetic field in the direction of magnetic moment. That's one of the causes assigned. But different scholars have different views to the cause of Earth's magnetism, exactly still not known. Now, some of the things that the Earth has an equator. This is the equatorial plane of the Earth. The Earth spins about this axis. The Earth spins about its axis. This is called the geographical axis. And at this position, we have what is called the Arctic Circle. And this is called the North Pole. Geographical north. It's called geographical north or true north. This extremity is called geographical south or true south. South pole or true south. So this is the North Pole, this is the South Pole. The Earth spins about this axis. This is the geographical axis. Now, what happens is, if you are at a certain point on the earth and you want to reach the North Pole. If you are at a certain point P on the surface of the earth and you want to reach the North Pole, you want to live a peaceful life, you want to go there somewhere. So now the question is, how do you reach the North? When you say, yeah, it's very easy. Very easy. If I want to reach the North Pole, I have a compass needle. The compass needle is like a rhombus shaped structure. And this is a magnetic needle. It has a north and south pole. And you say, I'll just go by the direction of this. The way it takes me, I'll reach the North Pole. This is what you will think. You'll go by the compass needle, the direction of the compass needle, and you'll think you'll reach the North Pole. You will not. You will not. If you keep following the compass needle, you would actually reach at some other point. You will reach some other point on the surface. Which means the north of the compass needle, does not point towards the geographical North Pole. Does not point towards the geographical North Pole. The deflection of this needle, you will reach some other point. You would reach, say, some P prime instead of the North Pole. This fellow, the compass needle, responds to it deflects based on the magnetic field of the Earth. Now the question is, so if it is responding to the magnetic field of the Earth, what point on the Earth will it take? According to this compass needle, what is the north? This is the geographical north pole, geographical south pole. But according to the compass, what is the north? What's the north or the magnetic north? This will take me to what is called the magnetic north of the Earth, not the geographical north. So then why? What happens? Well, it was originally believed when the whole science was evolving, science of terrestrial magnetism was evolving. It was believed that if this is the geographical axis about which it is rotating, it was believed that about this axis, the Earth along this axis behaves like a bar magnet, with this being the south of the bar magnet and this being the north pole of the bar magnet. It was believed that this is the case, that the whole Earth behaves like a bar magnet. Now, in a bar magnet, if you're aware, just to be on the same page, in a bar magnet, let's say this is the north pole and this is the south pole in a bar magnet. Then magnetic field lines, magnetic lines of force go from the north to the south. They leave the north and they enter the south. And magnetic field lines inside the magnet go from the south to the north. This is the magnetic field lines. And they are closed loops. Electric field lines will never be closed loop, but magnetic field lines are closed loops. Magnetic field lines are closed loop. In a bar magnet, magnetic field lines go from north to south. They leave north, they enter south. And inside also there is a completion of the magnetic field lines. Magnetic field lines inside the magnet go from south to north. Outside the magnet, they go from north to south. That's a bar magnet. Now, it was found that when the magnetic field lines, of the Earth were analyzed, it was found that from the south pole, they are going to the north pole. Magnetic field lines from the south pole, they are going to the north pole. This is the south pole. Which means the south pole is indeed not the north of the magnet. The south pole of the Earth is indeed the north pole of the magnet, which is this.
Yes, sir.
The north pole of the Earth, geographical north of the Earth, must be like the south pole of the magnet. Because, right?
Yes, sir.
Because magnetic field lines leave the north pole, magnetic north, and enter the magnetic south. तो साउथ पोल को लीव कर रहा है, मतलब साउथ पोल, geographical south pole must be like the north pole of the magnet. The Earth behaves like, and the geographical north pole, the geographical north pole must be like the magnetic south pole of the magnet that the Earth behaves like.
Yes, sir.
Yes, sir.
Okay. Very theoretically, the magnet that the bar magnet that the Earth behaves like is like this, with the north pole of that bar magnet being towards the geographical south pole of the Earth, with the south pole of that magnet being in the proximity of the north pole towards the Earth. After all, magnetic field lines will be generated by this.
Yes, sir.
Not by the north pole and the south pole, right? So obviously they have to leave the north pole of this bar magnet and enter the south pole. Yes or no?
Yes, sir.
Yes, sir.
Yes, sir.
So a very ideal assumption was that the Earth effectively behaves like a bar magnet placed along its geographical axis. The Earth behaves like a geographical bar magnet, behaves like a bar magnet with its magnetic south being closer to the geographical north pole of the Earth and its magnetic north being closer to the south pole or the geographic south pole of the Earth, so that from this north pole the magnetic field lines emerge. And but what really happened? So if this was the case, then and you know, the compass needle, the north pole of the compass needle should get attracted to the south pole of this magnet.
Yes, sir.
Yes, sir. Yes, sir. Yes, sir.
It is likely to take you to the south pole of this bar magnet, which is the north pole of the Earth.
Yes, sir. Yes, sir.
Right? It will get attracted not to the poles, it will get attracted to the poles of the magnet, the south and the north pole. Right?
Yes, sir. Yes, sir.
इससे तो तुमको नॉर्थ पोल पहुंच जाना चाहिए, which is the south pole of this bar magnet. पर ऐसा नहीं. You are not reaching the south pole of this magnet, which was the north pole of the Earth. That was not happening. One was getting deflected instead of by this needle. One was getting deflected. This north was not taking me to this north. It was taking me to some other point. Which means this bar magnet was not exactly along the axis of the Earth. This could have happened because this bar magnet that the Earth behaved like was not along the axis of the Earth. This was the axis of the Earth. Geographical north, geographical south. This was the axis. And the bar magnet that we saw is actually found to be tilted this bar magnet, with this being the south pole of the bar magnet, this being the north pole of the bar magnet, was actually found to be tilted. This magnet, which we assumed was along the axis of the Earth, was actually found to be tilted. It was the magnetic south was not towards the geographical north pole. The magnetic north was not exactly towards the geographical south pole. That was not happening. And this tilt between the and this axis where we could imagine the Earth to be like a bar magnet, is called the magnetic axis of the Earth. Magnetic axis of the Earth. This was the geographic axis. And this was the magnetic axis of the Earth. And the angle between them was not zero. This angle between them, angle between the magnetic axis and geographic axis, that does not remain constant. That varies with time. This angle, as of now, as it varies, it is different at different times. Today, as of now, it's roughly like 11.5 degrees. Roughly like 11.5 degrees. It varies from 11 to 20 degrees. It varies from 11 to 20 degrees. Angle between the magnetic axis and the geographic axis varies. Today, as of now, it's like around 11.5 degrees or so. But it's not fixed. But for our calculations, as and when required, we can assume it is around 11.5 degrees. Now,
স্যার স্যার ওটা মানে ফিক্সড নয় কেন, মানে এটার কোনো রিজন আছে
কোনটা?
মানে ওই স্যার ওটা মানে অ্যাক্সিসটা ফিক্সড নয় কেন, মানে ম্যাগনেটিক অ্যাক্সিস
আছে, কেউ জানেন।
আচ্ছা আচ্ছা,
ম্যাগনেটিক ফিল্ডের কারণই জানেন, অ্যাক্সিস কেন ইনক্লাইন্ড হবে সে কি করে জানে?
হ্যাঁ
কারণ আছে কিন্তু কেউ জানে না। ম্যাগনেটিক ফিল্ডেরই কারণ জানে না কেন হচ্ছে, why it is behaving like a bar magnet. Nobody knows. ऐसा नहीं कि there is an actual bar magnet, the effect it produces is like a bar magnet. আসলে এমন নয় যে সত্যিকার একটা লম্বা হাজার হাজার কিলোমিটার লম্বা একটা বার ম্যাগনেট আছে, সেরকম নয়। হ্যাঁ, মানে ওরকম একটা ইফেক্ট প্রডিউস করছে, বার ম্যাগনেটের মতন ইফেক্ট প্রডিউস করছে। এবার if you are at a point P on the surface of the Earth and you have your needle, I mean, এটা actually এর সাথে জড়িত একটা গ্যাপ দেখাচ্ছি just so that you know I can represent properly a gap.
Yes, sir.
Now if you have a magnetic needle now, যার নর্থ, এই ম্যাগনেটিক নিডলের নর্থ পোল এটা আর সাউথ পোল এটা।
Yes,
right? This magnetic needle, its attraction will be towards a magnet, not towards the north pole and the south pole, right? So this will obviously get attracted to the south pole of this magnet.
yes sir,
Yes, sir.
The north pole of this needle will get attracted to the south pole of this magnet,
yes sir,
Yes, sir.
right? So this magnetic needle, instead of taking you here, will take you to this point, which is the south pole of the magnet, south pole of this corresponding magnet. It will take you, actually, if you follow the needle, it will take you here to this point, this north, right? So this was my geographical north, and the south pole of this magnet, this end, we don't call it the south pole of the Earth, we call it the magnetic north of the earth, small n, small n. This end we call the magnetic north of the earth. This end we call magnetic south of the earth. However, for this bar magnet, the magnetic north of the earth and the magnetic south of this earth, for this magnet, this is the south pole of this magnet, this is the north pole of this magnet. Do you understand what I'm saying?
Yes, sir.
Magnetic north. So the north pole of this, the compass needle will take you to the magnetic north, which is actually coincident with the south pole of this bar magnet, south pole of this equivalent bar magnet. You know what I'm saying?
Yes, sir.
Yes, sir.
Confusion hai kya?
No, sir.
No, sir.
I mean, you might be tempted to believe कि भाई इसको why don't you call it just the south pole? Why don't you just call this the north pole? Because the magnet has, the convention is, because we've already called it the north pole and the south pole. तो उसके जो पास होगा ना उसको north pole ही बोलो, magnetic north pole बोलो. इसको actually ideally बोलना चाहिए था north pole of the magnet. हाँ, north pole ही बोलना चाहिए था, पर इसको हम south इसलिए बोलते हैं, magnetic south इसलिए बोलते हैं because it's closer to the geographical south. इसको magnetic north इसलिए बोलते हैं because it's closer to the geographic north. You know what I'm saying?
Yes, sir.
Yes.
है ना? But otherwise, from the perspective of the magnet, this is actually the south pole of this magnet, and this is actually the north pole of this magnet. Magnet के perspective से. पर convention ये है, we call it the magnetic north and we call this the magnetic south. ये convention form.
Yes, sir.
Yes, sir.
ठीक है? और जो magnetic needle, compass needle होता है, it will take me to the magnetic north, because the magnetic north is actually the south pole of this bar magnet, so it gets attracted to the south pole of this magnet, and that is what is happening.
Yes.
Yes, sir.
So this is the earth. This is the axis of rotation of the earth. And this is the geographic north pole. This is the geographic south pole. This is the geographical axis. The geographic axis. Right? The geographic poles and geographic axis. अब इसके पास होगा मैग्नेटिक नॉर्थ पोल और मैग्नेटिक साउथ पोल. दिस इज मैग्नेटिक नॉर्थ पोल and this is magnetic south pole. So the compass needle has, and the bar magnet is as if it's placed along this magnetic south pole. और बार मैग्नेट का जो अंदर रखा है उसका ये एक्चुअली साउथ पोल है और बार मैग्नेट का ये एक्चुअली नॉर्थ पोल है.
Yes.
Yes, sir.
Yes,
बार
sir.
मैग्नेट का अगर ये नॉर्थ पोल है और बार मैग्नेट का ये साउथ पोल है तो मैग्नेटिक फील्ड लाइंस यहां से निकलेगा और यहां जाएगा.
Yes.
हाँ,
sir.
sir.
मैग्नेट के नॉर्थ पोल से निकल के मैग्नेट के साउथ पोल में जाएगा, है ना?
हाँ, sir.
Yes, sir.
Yes, sir.
And like I said, this is the magnetic axis of the earth. And this, I said, this angle varies. Let's say it's 11.5 degrees. Right. Now, this is my geographic north. This is my geographic south. This is my axis of rotation. ये होता है geographical equator. ये होता है geographical equator, है ना? अब obviously दिख ही रहा है. अच्छा, ये इक्वेटर के ऊपर टुवर्ड्स द नॉर्थ पोल इस रीजन को क्या कहते हैं पता है? What is this hemisphere called?
Northern Hemisphere.
Northern hemisphere बोलते हैं उसको.
Northern Hemisphere.
ऊपर वाले को नॉर्दर्न हेमिस्फीयर बोलते हैं और नीचे वाले को इक्वेटर के नीचे टुवर्ड्स द जियोग्राफिक साउथ
Southern Hemisphere.
है ना?
हाँ सर.
Yes, sir.
अभी ज्योग्राफी में नहीं सीखे थे, फिजिक्स में सीखे. I had such a bias when they were teaching all of this in geography. I did not know, but when I became a student of physics, that's when I came to know this. So that's called a bias towards a subject. Now, obviously, ये तो मालूम पड़ रहा है. मैग्नेटिक फील्ड लाइंस होगा ना, ये मैग्नेट का नॉर्थ पोल है, ये मैग्नेट का साउथ पोल. तो ऑब्वियसली मैग्नेटिक फील्ड लाइंस will emerge from the southern hemisphere और ऊपर जाके northern hemisphere में, है ना? क्योंकि मैग्नेट का नॉर्थ पोल यहाँ है, तो यहाँ से southern hemisphere से निकलता है मैग्नेटिक फील्ड लाइंस और northern hemisphere में बैठता है. Yes or no?
Yes
sir.
sir.
Yes, sir.
Magnetic field lines come from the southern hemisphere, exit out of the southern hemisphere and enter the northern hemisphere. Magnetic field lines. Yes or no?
Yes, sir.
Yes, sir.
Yes sir.
Magnetic field lines exit the southern hemisphere and enter the northern hemisphere. मतलब मैग्नेटिक फील्ड लाइंस नॉर्दर्न हेमिस्फीयर पे कोई पॉइंट लोगे ना तो लगेगा अंदर आ रहा है. सदर्न हेमिस्फीयर पे कोई पॉइंट लोगे तो मैग्नेटिक फील्ड लाइंस लगेगा बाहर आ रहा है. मतलब द मैग्नेटिक फील्ड at a point on the southern hemisphere will go out. At a point on the northern hemisphere, the magnetic field BE is the magnetic field of the earth. Different at different points. तो सदर्न हेमिस्फीयर में बीई बाहर जाएगा और नॉर्दर्न हेमिस्फीयर में कोई भी पॉइंट लोगे उसमें बीई मैग्नेटिक फील्ड अंदर की तरफ जाएगा. बिकॉज़ राइट.
Yes
Yes,
sir.
Yes, sir.
Now सोचो, say we take a point on the northern hemisphere, point P on the northern hemisphere. Say, can I wipe this portion off?
Yes
Yes,
sir.
sir.
ये surface of the earth है, horizontal surface of the earth on the northern hemisphere. Horizontal surface of the earth, and P is a point on the northern hemisphere. Northern hemisphere में क्या होगा? Magnetic field अंदर की तरफ आएगा. BE magnetic field will be like this, right? BE. Magnetic field will be of magnitude BE going will make an angle, say delta with the horizon. BE at P makes an angle delta with the horizon. सदर्न हेमिस्फीयर में अगर कोई पॉइंट पी होगा, अगर सदर्न हेमिस्फीयर में कोई पॉइंट होगा, एनी पॉइंट ऑन द सदर्न हेमिस्फीयर, this is the horizontal surface at P. P is a point on the southern hemisphere, तो BE बाहर निकलेगा, है ना, क्योंकि मैग्नेटिक फील्ड है सदर्न हेमिस्फीयर से निकल के नॉर्दर्न हेमिस्फीयर में जा रहा है, and this will be the angle delta with which the magnetic field makes with the horizontal in either case.
Yes, sir.
Yes, sir.
So the angle made by the magnetic field at the with the horizontal at P is called the angle of dip. Angle of dip at P. Angle of dip at P. It's called the angle of dip. What important? It's called the angle of dip at P.
Yes, sir.
Yes.
For different points on the surface of the earth, this angle will be different. Different. ये जो एंगल ऑफ डिप है ये डिपेंड्स ऑन वेयर दिस पॉइंट इज.
Yes, sir.
Yes, sir.
So whether northern or southern hemisphere does not matter. Suppose I take a point P in the northern hemisphere. उसमें BE कैसा है? BE is going like this on the northern hemisphere, right?
Yes,
Yes,
sir.
sir.
This is the horizontal direction, and this will be the vertical direction at P, right?
Yes, sir.
This is the angle of dip delta. That means ये देखो, ये भी delta होगा alternate angles.
Yes, sir.
So
Yes, sir.
BE can be resolved. ये delta है ना, in two directions. Horizontal direction BH and vertical direction BB. BH and BB are horizontal components of the magnetic field. Now, can you see that if B is the magnetic field at B and delta is the dip, you can know from various graphs, dip will be given to you. The dip at every point, delta. From the dip, you can find the horizontal component. BE दिया है और dip दिया है, तो horizontal component क्या होगा? BE cos delta.
Yes, sir.
Yes,
sir.
sir.
And BB क्या होगा? BE sin delta.
B sign.
Right? Where delta
Yes,
is
sir.
the dip at the point P and B is the magnitude of the magnetic field, terrestrial magnetic field at the point P. Very clearly, BE square will be BH square plus BD square.
Yes, sir.
This is the horizontal, this is an important thing, horizontal component of BE. Very important, this especially the horizontal component of the magnetic field. BE is obviously magnetic field of the earth. Obviously, if I square and add, BE would be root BH square plus BV squared. Also, if I divide this by this, then tan delta, tan of the angle of dip would be vertical component of the magnetic field divided by horizontal component of the magnetic field. Tan delta, tan of the angle of dip would be vertical component of the magnetic field at that point divided by the horizontal component of the magnetic field at that point. Okay.
Yes, sir.
Yes, sir.
एक्चुअली क्या होता है, ये एक पॉइंट है, ठीक है, और ये हॉरिजॉन्टल प्लेन है अराउंड दैट पॉइंट ऑन द सरफेस ऑफ द अर्थ. यहाँ पे BE ऐसा जा रहा है. BE will have a horizontal component and BE will have a vertical component. Suppose BE अंदर की तरफ जा रहा है northern hemisphere में, so this BE will have a horizontal component going this way, will have a vertical component this way. Now यहाँ पे suppose on the horizontal plane I place a magnetic needle. जो कंपास नीडल होता है, I place it horizontally on this. उसका नीडल किस तरफ पॉइंट करेगा? That needle will point because it has no capability to rotate. That needle has no capability to rotate vertically. अगर ऐसे रखेंगे, that needle has no capability to rotate vertically, तो वो needle horizontally rotate करेगा. If it rotates if the needle rotates only horizontally, it will point towards the horizontal component of the magnet. सोचो नीडल है, यहाँ पे ये नीडल है, उस पे रखा है, ठीक है. अब नीडल आइडियली तो नीडल शुड पॉइंट टुवर्ड्स BE.
Yes,
पर
sir.
नीडल तो वर्टिकल प्लेन में रोटेट ही नहीं करने दे रहे हो, तुम उसको खाली बोल रहे हो बेटा हॉरिजॉन्टल कंपोनेंट में रोटेट करके अपना पोजीशन ले, फायर कर. उसके बाद तो वो रोटेट करेगा ना कंपास नीडल, तो वो क्या करेगा ना, इट विल अलाइन इटसेल्फ अलोंग BH. द कंपास नीडल प्लेस्ड हॉरिजॉन्टली एट P. यहाँ पे P है, ये हॉरिजॉन्टल प्लेन है और BH इस तरफ है. Then the compass needle will align itself along BH. Ideally, अगर if it was capable of rotating both vertically and horizontally, ऐसे भी rotate कर सकता होता था और ऐसे भी अगर rotate करता, then it would point, then the compass needle will point towards B. A compass needle will always want to get aligned in the direction of the magnetic field.
Yes, sir.
You are not allowing that, so it says okay, I'll settle for getting aligned along BH. Okay.
Yes, sir.
Yes, sir.
Now, so you understand what angle of dip is.
Yes, sir.
And now, this is the Earth. ये इसका जियोग्राफिकल नॉर्थ पोल है, ये जियोग्राफिकल साउथ पोल है. ये जियोग्राफिकल एक्सिस है और ये मैग्नेटिक एक्सिस. MA इज मैग्नेटिक एक्सिस एंड अच्छा मैग्नेटिक एक्सिस में वो जो अंदर का मैग्नेट है उसका ये साउथ पोल है, पर इसको मैग्नेटिक नॉर्थ कहते हैं, इसको मैग्नेटिक साउथ कहते हैं. This is the magnetic north, this is the magnetic south, right? Now, if I take a point P on the surface of the earth, if I take a point P on the surface of the earth, ठीक है बेटा?
हाँ, sir.
At that point P, तो of course true north and true south फिर भी geographically बोलते हैं, ठीक है?
हाँ सर.
ये फिर भी true north true south है, ये magnetic north magnetic south. Now if I take a point P on the surface of the earth, suppose this was a point on the surface of the earth. This was my geographical north. ये कोई पॉइंट लिया और यहाँ पे ये मेरा मैग्नेटिक नॉर्थ, geographical north. And this is magnetic north. Now, अच्छा तुम मेरे को बताओ, अगर इसको डायमीटर लेके एक सर्कल बनाएंगे NS को, कितना सर्कल बन सकता है?
Infinite.
इस प्लेन में एक ही सर्कल बनेगा, बट अगर ये कोई डायमीटर बोला तो यू नो आई कैन हैव अ सर्कल लाइक दिस, आई कुड हैव हैड अ सर्कल लाइक दिस, I could have had a circle like this. Infinity of circles.
Yes, sir.
On the plane of the board एक ही सर्कल बनेगा, but otherwise एक लाइन दिया डायमीटर है उसको infinity circles बना सकते हैं, ऐसे 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 rotate.
Yes, sir.
But if I say इसको डायमीटर लोगे, एक सर्कल ऐसा बनाओ जिसका डायमीटर ये है and it also passes through P, then how many circles can you have?
One.
Because now there are 3 points, N, S and P. It will uniquely determine a circle.
Yes, sir.
Yes,
Yes,
और एक
sir.
सर्कल फिर एक प्लेन में ही रहेगा.
हाँ sir.
yes, sir.
So that circle determines a plane, right? With NS geographical along with a point P on the surface, a unique circle can be drawn. The unique circle can be drawn, which lies in a certain plane. वो circle, हर circle determines a plane, ना? There is a plane that it determines, which lies in a plane. That circle will lie in a plane, right? Such a plane is called the geographic meridian. At P. समझ गए क्या? एक ऐसा प्लेन बनाओ which passes through NS and P. 3 पॉइंट से प्लेन यूनिकली डिटरमिन हो जाए.
हाँ sir.
हाँ sir.
NS और P से वो सर्कल जो बनाओगे, that will be a certain plane, because the
Yes.
circle is a planar figure. So there is that plane is the geographic plane at the point P.
Yes sir.
Is the geographic meridian at the point P. Is the geographic meridian at P, right? So at every point
Yes.
P, for different points P, you will have different geographic meridians, different planes, right?
Yes,
Yes.
sir.
Yes, sir.
With magnetic north-south and P, a circle could be drawn. मतलब ये मैग्नेटिक नॉर्थ साउथ और P से एक सर्कल बना सकते हो, यूनिक सर्कल
Yes sir.
describing a certain plane. Vertical plane, describing a certain vertical plane. And P, उसको कहते हैं मैग्नेटिक मेरिडियन और अ मैग्नेटिक मेरिडियन. Called a magnetic meridian. So at every point P, there is a geographical meridian, which is a certain plane, and there is a magnetic meridian at that point. There are two meridians, a geographic meridian and a magnetic meridian at every point of the surface, right?
Yes, sir.
Yes, sir.
Yes, sir.
Now, let me come down to, so what we do is, this is my geographic north, this is my magnetic north. This is my geographic north, this is my magnetic north. Okay. What I do is, passing through N, P, and of course the geographic south, यहाँ पे geographic south कहीं पे यहाँ पे है. I draw a plane, right? PN, एक vertical plane. This is a vertical plane containing magnetic north, south, and ये एक vertical plane है that contains the magnetic north. ये वाला magnetic north will also contain the magnetic south and the point P. It's a vertical plane containing this axis and the point P.
Yes, sir.
Yes, sir.
Yes, sir.
इसी plane को जो हमने बताया था, it's called a magnetic meridian. It's a magnetic meridian. This is a magnetic meridian. This plane is really the magnetic meridian. Okay.
Yes, sir.
Yes, sir.
Now, this is the geographic north. ये जो दूसरा प्लेन है, geographic north, geographic south and P से पास करता हुआ जो vertical plane, that will be called a geographic meridian. मतलब वो प्लेन ऐसा. That plane. समझ रहे हो? Can you visualize that?
Yes, sir.
Yes, sir.
Yes, sir.
I hope you can understand. इस टाइप का सोचो. ये पॉइंट P है, इसमें ऐसा. ये मैग्नेटिक मेरिडियन है. This is the magnetic meridian. यहाँ और सोचो ये पीछे वाला पेज है वो geographic meridian है, right?
Yes, sir.
Yes, sir.
Yes, sir.
Right? And the point P is here. So obviously, this and this are horizontal directions. P और N को join करना और P और small n को join करना. These are horizontal directions.
Yes, sir.
Yes, sir.
Yes, sir.
At P, the horizontal component of the magnetic field will lie like this,
Yes, sir.
Yes, sir.
right? The
Yes, sir.
vertical component will lie like this. These are vertical planes.
Yes, sir.
Yes, sir.
So what happens is, the horizontal component of the magnetic field will lie like this at some point, and the vertical component of the magnetic field will lie like this. Yes or no?
Yes, sir.
ये मैग्नेटिक मेरिडियन है और ये पीछे वाला क्या है? ज्योग्राफिक मेरिडियन. ज्योग्राफिक मेरिडियन ये वाला जो डॉटेड लाइंस पे दिखा है, दिस इज द ज्योग्राफिक मेरिडियन एट पी. इसका मैग्नेटिज्म से कोई लेन देन नहीं है क्योंकि मैग्नेट तो यहां प्लेस है. ज्योग्राफिक मेरिडियन. एम आई कंफ्यूजिंग यू?
No, sir.
No, sir.
No,
No,
sir.
sir.
अब ये देखो ये दोनों प्लेन्स, ये P और N लाइन और P और स्मॉल n लाइन, दिस विल गिव मी द एंगल बिटवीन द टू प्लेन्स,
Yes, sir.
Yes, sir.
Yes, sir.
राइट? दिस हॉरिजॉन्टल डायरेक्शन और दिस हॉरिजॉन्टल डायरेक्शन, इन दोनों के बीच में जो एंगल होगा दैट विल आल्सो बी द एंगल बिटवीन द ज्योग्राफिक मेरिडियन एंड द मैग्नेटिक मेरिडियन. दिस इज द मैग्नेटिक मेरिडियन, दिस इज द ज्योग्राफिक मेरिडियन, राइट?
Yes, sir.
Yes, sir.
Angle. So invariably there will be an angle between these two planes, alpha. Angle between the magnetic meridian and the geographic meridian. At P, alpha is angle between the geographic meridian which is a plane ऐसा and magnetic meridian. ये magnetic meridian है, magnetic meridian and is called the angle of magnetic declination. It's called, this alpha is called magnetic declination or angle of declination. Magnetic declination or angle of declination at P is different at different points. On the surface. तो तुम अगर C में जा रहे हो, then do you realize the magnetic compass will point in the direction of the magnetic north? इस direction में point करेगा.
Yes, sir.
Horizontal magnetic compass will point in this direction.
Yes, sir.
Therefore, take you to the magnetic north.
Yes, sir.
yes
But
sir.
अगर तुमको पता है alpha at the point P, if you know alpha at the point P, then you know कि कितना धोखा हो रहा है. Alpha is the amount of धोखा that the needle is giving you.
Yes, sir.
Yes, sir.
तुम उतना rotate कर लोगे. C का में जा रहे हो, you will rotate your steering by about alpha so that you can reach the geographic north. So
Yes, sir.
the compass is doing its job. It's taking you to the magnetic north. And then angle of declination is known to you at that point on the surface of the earth. Then you know that you need to rotate by an amount alpha so that you can reach the geographic north.
Yes, sir.
yes sir.
Right?
Yes, sir.
স্যার অ্যাঙ্গেল অফ ডিক্লিনেশনটা তো মানে ডিফারেন্ট পয়েন্টস এর জন্য ডিফারেন্ট। তাহলে স্যার মানে একটা পয়েন্ট দিয়ে ধরুন শুরু করলাম, তো তাহলে তো স্যার মানে সব পয়েন্টেরই জানতে হবে মানে।
অ্যাকচুয়ালি সেটাও বলছি, কি হয় আর্থের একটা ডেক্লিনেশন ম্যাপ হয়, ডেক্লিনেশন ম্যাপ। ওই ম্যাপে কি হয়, there is a declination map, এই আর্থের ম্যাপ হবে। There are and several points P can have the same declination. Several points P on the earth will have the same declination. Locus of points P on the surface of the earth having the same declination alpha is called isogonic lines. মানে এই ম্যাপে কি দেওয়া থাকবে, তোকে আইসোগনিক লাইনস ভাব, এই ব্লু কালারের একটা লাইন আছে, all points, you know the position of these points, you will know that you lie here. As of now, you are at this point of the earth.
Yes sir.
A point A and this, all these points on the surface of the earth are, let's say, for alpha equal to 20 degrees. Angle of declination is 20 degrees. Then you know that you need to rotate by 20 degrees if you are at this point. Then there can be these are set of points on the earth where alpha is 15 degrees. মানে তোকে ওই ম্যাপটা দেখতে হবে, ওই ম্যাপে দেখবি তুই কোথায় লাই করছিস আর ওই লাইনে কত অ্যাঙ্গেল অফ ডেক্লিনেশন আছে,
হ্যাঁ হ্যাঁ স্যার,
বুঝতে পারছিস?
হ্যাঁ হ্যাঁ স্যার বুঝতে পারছি।
And these lines are isogonic lines, different points on the surface of the earth, set of points with alpha equal to 20 degrees. This is set of points with alpha equal to 15 degrees. There can be set of points with alpha equal to 5 degrees and so on so forth.
Yes sir.
Right? These are called isogonic lines, lines of same alpha. These are called lines for a curves hi ache, but lines hi bole. These are lines of constant alpha, same alpha, and they are called isogonic lines. Amongst these isogonic lines, there is a line, there is a set of points where the angle of declination becomes 0. there are set of points on the surface of the earth, এই point গুলো মানে এখানে এটা graphical depiction on these points corresponding to these latitudes and longitudes, the angle between the geographic meridian পেছনের দিকে যাচ্ছে আর এটা magnetic meridian is 0 degrees. যখন এই আলফাটা 0 হয়ে যাবে, then the magnetic meridian at that point flushes with the geographic meridian. This line, this set of points, this line is called an agonic line. Agonic line, where alpha is 0 amongst the isogonic lines. Amongst the isogonic lines, there is a line which is the locus of points where alpha becomes 0. Such a line is called an agonic line. Such a line is called an agonic line amongst the isogonic lines, right?
Yes, sir.
Yes,
তো এই
sir.
ম্যাপ থেকে বোঝা যাবে তুই কোথায় আছিস আর সেই পয়েন্টে দেখবি কোন আইসোগনিক লাইনে আছিস।
হ্যাঁ হ্যাঁ
You know what is the amount you need to deflect. কেন কম্পাস তো তোকে ম্যাগনেটিক নর্থে নিয়ে যাবে, তুই যেতে চাস জিওগ্রাফিক নর্থ, রাইট?
yes sir.
Yes, sir.
Suppose to, you know, this is the true north, matlab true north direction, this is the true south direction, this is the true east direction, this is the true west direction, right?
Yes, sir.
Yes sir.
And there is a compass. So you are at this point, উপর থেকে দেখছিস পুরো জিনিসটা,
Yes sir.
horizontal plane, উপর থেকে horizontal plane দেখছিস, and you find, so your compass needle could be like this, showing you north like this, north south. So is it showing you the geographical north? No, it is showing you the
Magnetic north.
magnetic north. And suppose alpha at this point is 8 degrees east. তার মানে এই true north direction থেকে deviation হচ্ছে 8 ডিগ্রি ইস্টের দিকে। Magnetic north is deviated from true north 8 degrees east.
আচ্ছা আচ্ছা হ্যাঁ স্যার।
এবার ম্যাগনেট তোকে বলছে এরকম যা, আলফা জানা আছে 8 degrees east, সেখান থেকে তুই 8 ডিগ্রি ইউজ করে you can find out the true north direction,
Yes, sir.
Yes sir.
right? You can find out the true north direction. Got me?
Yes sir.
Yes, sir.
Sometimes say this is true north, true east, and the compass needle points like this. This is magnetic north. It is pointing towards the magnetic north. And the alpha at this point supposes 8 degrees west. That means 8 degrees west of north. This is that means 8 degrees. And then you know that you have to move 8 degrees like this to head in the true north direction.
True north. Yes sir.
বুঝতে পারছিস ব্যাপারটা?
হ্যাঁ হ্যাঁ sir.
Okay. Now, stay like that. At the point P, this is the magnetic meridian, and this is the পেছনের দিকে geographic meridian. This is the magnetic north. This is the geographic north. Okay.
Yes sir.
The horizontal component of the magnetic field is towards the magnetic north.
Yes, sir.
Yes sir.
Yes, sir.
The compass needle will point towards, and this is the horizontal direction, right? These two are horizontal lines on the surface of the earth. So BH will be like this, and this both are vertical planes. So BD will be like this at the point P, right?
Yes sir.
Yes, sir.
And this is the magnetic meridian. That means the net magnetic field will be in the magnetic meridian. Yes or no? Do you see that?
Yes.
Yes, sir.
The net magnetic field will be in the magnetic meridian. है ना? BH और BD का resultant magnetic meridian में होगा ना?
Yes sir.
Oh, sir.
Resultant of BH and BE, which is BH and BD, which is BE, is in the will lie in the magnetic meridian. Magnetic meridian at P क्या होता है? एक vertical plane passing through P and containing the magnetic north. Geographical meridian क्या होता है? A plane passing through P, a vertical plane passing through P, containing the geographic north and the point. Right? Which means a compass needle will show, if allowed, will be along B. But if not allowed, if it is kept only horizontal and is not allowed vertical deflection, then the compass needle will move along BH. अब देखो, तो यहाँ पे do you realize the angle that BE makes with the horizontal will be the angle of dip.
Yes, sir.
So इस figure में the angle of dip is this much. Angle of dip किसमें देखेगा? Magnetic meridian में देखेगा angle of dip.
Yes,
sir.
Yes, sir.
तो BH क्या हो जाएगा? BE cos delta. BD क्या हो जाएगा? BE sin delta. Delta angle of dip can be visualized only on the magnetic meridian. Magnetic meridian क्या है? Plane है. A vertical plane passing through P and the magnetic north. Alpha क्या होगा? Angle of declination. Angle between the geographic north and magnetic north. You know what I'm saying?
yes,
Yes, sir.
Yes, sir.
These are two important things, alpha and delta.
Yes, sir.
अब अगर ना सोचो ये कंपास needle and this is a compass needle. So this is the compass needle at the point P. यहाँ पे just above a point P and it's suspended freely. Compass needle is suspended freely. सोचो यहाँ से at P a compass needle is suspended freely. ऐसे ये compass needle freely suspend किया उसको. ठीक है?
Yes, sir.
yes, sir.
If this compass needle is allowed only horizontal deflections, it will point towards BH. But if you allowed horizontal as well as vertical deflection, this compass needle, if it is allowed to swivel like this as well as like this, तो क्या होगा जानते हो? वो compass needle, first the compass needle will get aligned with the magnetic meridian. सबसे पहले ऐसे उलट पुलट है वो compass needle. पहले क्या हो जाएगा? It will align itself along the magnetic meridian. फिर क्या करेगा वो compass needle dip कर जाएगा along B. You know what will happen?
Yes,
If given
sir.
all freedom, the compass needle will first get aligned along the magnetic meridian. This is my magnetic meridian, and then it will dip. It will dip like that's why it's called the angle of dip, because in the vertical direction the compass needle will dip by an amount delta in the magnetic field. इसीलिए इसको angle of dip बोलते हैं. You know what I'm saying?
Yes, sir.
Yes, sir.
Freely suspend कर
Yes,
दो,
sir.
what will happen? This compass needle will first become parallel to the magnetic meridian. उसके बाद वो dip कर जाएगा so that it will point towards B. Yes or no?
Yes, sir.
Yes, sir.
Alpha, the angle of declination, and dip, delta. Delta is roughly 0 at the equator and is roughly 90 degrees at the poles. Equator पे क्या होगा? Delta 0 हो जाएगा. So the magnetic field will be parallel to the horizontal.
Yes, sir.
Yes, sir.
और delta 90 degrees हो जाएगा at the pole. That means at the pole it will be perpendicular to the surface.
Yes, sir.
Perpendicular to the horizontal. पोल्स में मैग्नेटिक फील्ड परपेंडिकुलरली एंटर करेगा, इक्वेटर में पैरेलल टू द सरफेस आ जाएगा,
Yes, sir.
Yes, sir.
राइट?
Yes, sir.
So you understand this alpha, delta, and horizontal component of the magnetic field of the earth.
Yes, sir.
Yes, sir.
With this
No,
No,
sir.
sir.
No, sir.
terrestrial magnetism, if you know this much, that will do. All right, now let me teach a few more things that we require. Okay,
Yes, sir.
Yes, sir.
trust me, if you've learned this much of terrestrial magnetism properly, angle of dip you understand, angle of declination you understand, and the horizontal component of the magnetic field you understand, and the fact that the magnetic meridian is a position of equilibrium for a freely suspended compass needle. You understand those things, and that BE will lie purely along the magnetic meridian. You're doing great. All right.
Yes, sir.
Yes, sir.
I mean, I could have just gone ahead and taught you a little more on this, but that's like unnecessarily adding burden to you. You already have so many things to do. So let me not add burden. Let me teach you some more things. Very simple things. So if you recall, when I just started magnetism with you, I said in a magnet, some of the, it's a typical bar magnet, there is a south pole and there is a north pole. Right? In a typical magnet, there is a south pole and there is a north pole. And although approximately we take south at the extreme end and north at the extreme end, that does not happen. It's slightly away from the ends. Also, each pole has a strength. If this north pole has a strength plus n, pole strength. And this south will then have a pole strength minus n in a given magnet. This pole strength will depend on the following: the material of the magnet. 2, it will depend on the area of cross section. ये area of cross section पर depend करेगा. Area of cross section, extent of magnetization. After all, this magnet has been created by magnetizing it, right? By exposing
Yes,
it to a magnetic field, it has been magnetized. So the extent of magnetization. If 2L is the length, pole strength will not depend on the length. इस एरिया ऑफ क्रॉस सेक्शन को आधा कर दोगे तो पोल स्ट्रेंथ आधा हो जाएगा. सेम मटेरियल, एवरीथिंग रिमेनिंग द सेम. ठीक है?
Yes, sir.
Yes, sir.
Will not depend on the length, say 2n. In a horseshoe magnet kind of a thing. This is what we have: n south plus n magnetic strength. We define the magnetic moment. Then, in this case, the length 2L will be this taken. Magnetic moment M is a vector directed from south to north. From south to north. Magnetic capital M is magnetic moment of this magnet. The magnetic moment of this magnet is a vector whose direction is from south to north. from the south pole to the north pole, and with magnitude M equal to pole strength into 2L. Pole strength is the pole strength into the length. Pole strength into the length. Right?
Yes, sir.
Yes, sir.
Now, also I told you, although we cannot isolate poles, but if I imagine two poles of pole strength M1 and M2, then two poles with pole strength M1, isolated poles, theoretically नहीं, ये actually possible नहीं, but theoretically imagine करें, then the force between the two poles F would be given by mu naught by, इसमें K electrostats में K होता है 1/4 pi epsilon naught, इसमें K की जगह mu naught by 4 pi होता है, like I told you, into M1 M2 by the distance R. The inverse square law field. And if I imagine an isolated pole F, it will produce a magnetic field at this point. It will produce a magnetic field at this point at a distance R. It will produce a magnetic field which is mu naught by 4 pi K Q by R square होता है, ये M by R square, which is the force experienced by a magnetic north pole of unit pole strength. मतलब M1 की जगह M डाल दो, M2 is pole strength 1 of a north pole, वहां पे force experienced by unit positive charge होता है, यहाँ पे this magnetic field is the force experienced by a north pole of unit pole strength, force experienced by a north pole of unit pole strength B होता है, mu naught by 4 pi M by R squared होता है, magnetic field created by M. By a pole M of pole strength, right? अगर ये medium does not have permeability mu naught, तो mu naught into mu R हो जाता है, पर mu R is the relative permeability.
Yes, sir.
Multiply करते हैं अगर कोई और medium हो vacuum की जगह. In vacuum this, otherwise mu R से multiply करते हैं relative permeability.
Yes.
Now, also, if a pole of strength and pole strength then is placed in a magnetic field B naught, then it experiences a force F equal to M into B. B naught is the force experienced for a unit pole, for a pole of pole strength, then this is the force experienced. Okay? So a pole can create its own magnetic field, and when placed in a magnetic field, it can experience a force, right?
Yes, sir.
Now, let me look at what I refer to as a magnetic dipole. Electrical dipole पता है? A pair of charges separated by a very small distance. Pair of charges equal and opposite, plus q and minus q, separated by a very small distance, right? अगर एक सोचो बार मैग्नेट है ना, it can be looked upon as a magnetic dipole. सोचो एक बार मैग्नेट है, imagine a bar magnet. South pole, north pole. Pole strength minus m है इसका और pole strength plus m है इसका. ये magnetic axis और ये length 2l. If 2l is very small, it's almost like a magnetic dipole. If 2L is very small, it's like a magnetic dipole. Right? जो भी है magnetic dipole moment of this m of this क्या होगा? M into 2L is the magnet and will be from south to north. Will be from south to north. Right? That's the magnetic moment. Now, for a bar magnet minus m plus m, I want to be able to obtain the field at a point P to get the created by the bar magnet at P. Field will be in the direction of the force experienced by a isolated unit north pole. Isolated unit north pole. That will give me the direction of it. अच्छा, अब इसमें क्या है? There is the field at this point P will be because of this north pole and will be because of this south pole of pole strength minus m. Yes or no?
Yes, sir.
Yes, sir.
Yes, sir.
So, if I keep a unit north pole here, it will experience repulsion from this,
Yes, sir.
Yes, sir.
and therefore the magnetic field because of the north pole will be like this. Magnetic field because of the north pole will be to the right, and the magnetic field because of the south pole. See, if I keep a unit north pole here, it will get attracted to this.
Yes, sir.
Yes, sir.
The field because of the south pole will be BS like this. Because of south pole of the magnet. So the net field at अच्छा Bn क्या हो जाएगा? KQ by R squared होता है. अब Q की जगह M रहेगा और K की जगह mu naught by 4 pi रहेगा. So it's going to be K, which is mu naught by 4 pi. Instead of charge, I'll have the pole strength divided by, suppose इसका एक midpoint ले लेते हैं. वहां से ये distance, suppose this distance is D, and this is L by 2. No, this is L. Say L. L है, ये भी L. Right. So how much is the distance from this north pole to this point? D minus L.
Yes,
ये
sir.
D minus L है. So
Yes, sir.
F by D minus L whole square is the magnetic field produced by this north pole at this point will be in this direction. K Q की जगह M by D minus L whole square. Yes or no?
Yes, sir.
Yes, sir.
Because of the south pole, the magnetic field is in this direction. Because
Yes, sir.
if I keep the north pole here, it will get attracted to the south pole. BS will be what? BS will be the magnetic field in this direction created by this K, which is mu naught by 4 pi. If अगर A की जगह कोई और medium होता तो mu naught into mu r. Q instead of Q, I'll take the pole strength M by, now what is this distance? Distance between P and S. See, this is
D plus L.
D plus L, right? So D plus L whole square. Net field at P is Bn minus Bs, right? Bn minus Bs would be the net field at P.
Yes, sir.
It should be mu naught by 4 pi M into 1 by D minus L whole square minus 1 by D plus L whole square. Plug in किया? Yes or no?
Yes, sir.
Mu naught M by 4 pi D plus L whole square. So ये 4DL हो जाएगा. D plus L whole square minus D minus L whole square denominator में आ जाएगा. D squared minus L squared to power 2. Yes or no? Now, if M into 2L is the magnetic moment,
Yes, sir.
तो यहाँ M into 2L ले लोगे तो m आ जाएगा, तो 2md आ जाएगा ये,
हाँ
हाँ
सर
सर,
क्योंकि m into 2l कैपिटल M हो जाएगा, मैग्नेटिक मोमेंट ऑफ दिस मैग्नेट into d, so 2md हो जाएगा ये,
यस सर।
हाँ सर
times magnetic moment into d, so mu naught by 4 pi 2 times the magnetic moment, small m into 2l into d divided by d square minus l square whole square. Yes or no?
yes sir,
Up there. And now approx. So this is the result. Mu naught by 4 pi 2md. M is the magnetic moment, pole strength नहीं, M is the magnetic moment of this bar magnet, d square minus l square, और नीचे का square, right? अब देखो, if d is much larger than L, if d is much larger than L, मतलब this point is much further away than the size of this magnet. If d is much larger than L, then d square minus L square will be roughly d square only. L बहुत छोटा है, तो ये बहुत बड़े नंबर में से उससे relatively छोटा नंबर निकाल दोगे ना, तो वो d square के बराबर ही हो जाएगा ना.
यस सर।
हाँ सर,
So this is roughly d square, so I can replace this by d square.
यस सर।
yes sir,
Then Vp is mu naught by 4 pi 2md. अब ये L square neglect कर दो क्योंकि L बहुत छोटा है, तो this will become like a d to power 4, so which is like mu naught by 4 pi into 2m by d. M is the magnetic moment of this bar magnet, and d is the distance of this point from the magnet. M is the magnetic moment, d is the distance of this point from this magnet. अब ये d है ना, actually ये इस end से भी हो सकता है, इससे कोई फर्क नहीं पड़ेगा क्योंकि L बहुत छोटा है. So it's not necessary that it should be from the midpoint. It could be from anywhere because, right? Do you understand what I'm saying?
yes
This is
sir,
almost like a point magnet. ये बहुत
Yes,
छोटा
sir.
है compared to this distance. So you have to remember this mu naught by 4 pi into 2m by d cube. This is this point P. This point P is called the end-on position. यहाँ पे, okay, end पे है ये. There is another position. Can I wipe this off?
यस
And
सर।
yes sir,
it is in the direction of the magnetic moment. इस तरफ है because Bn larger than Bs. It's in the direction of the magnetic moment. Magnetic moment is also like this. From south to north. ठीक है?
স্যার নিচের ওই একটা লাইন দেখা যাচ্ছে।
In the direction of the magnetic moment M of the.
আচ্ছা আচ্ছা, হ্যাঁ হ্যাঁ ঠিক আছে।
হ্যাঁ, মানে magnetic moment তো south থেকে না, এটাও in this direction.
यस
मुझे दी.
यस सर।
yes sir
एक और पोजीशन होगा. South, north, magnetic pole strength M, magnetic pole strength minus M. अब ये perpendicular bisect, perpendicular bisect. This is L, also L. I take a point P, distance D like this. At this point हमको निकालना है. Okay. Now, the magnetic field at P again, like before, magnetic moment is going to be M into 2L. Is the magnetic moment of this from south to north, right? अब at P, If I place a unit north pole, it will experience repulsion from this in this direction.
Yes, sir.
The magnetic field because of the north pole will be like this, right? Because of the
Yes, sir.
south pole, if I place a unit north pole here, it will get attracted to the south pole.
Yes, sir.
Magnetic field because of the south pole will be like this.
Yes, sir.
Bn और Bs का magnitude same है, because this and this are the same. Realize Bn in magnitude is the same as Bs. Both mu naught by 4 pi k q की जगह m same है, divided by this square or this square is the same, right?
Yes, sir.
Square. If this angle is theta, this will also be theta, and this will also be theta. Yes or no?
Yes,
B or
sir.
Bs will be B like this. B at the point P, the resultant will, because the vertical components of Bn and Bs will cancel,
Yes, sir.
Yes, sir.
right? So Bn cos theta plus Bs cos theta. The net field at P opposite to M, because in this case N is like this and this is opposite to M. Opposite to M. M is from south to north, so this is opposite to M and parallel to the magnet.
Yes, sir.
Yes, sir.
So अब ये देखते हैं क्या है. Bn is what? mu naught by 4 pi m by L square plus d square. That's Bn. And cos theta is what? Cos theta is L by root L square plus d square, right? L by root L square plus d square. Cos theta. Mu naught by 4 pi. Again, 2 ml will be the magnetic moment of this magnet.
Yes, sir.
Well, right? So m divided by L square plus d square to power 3 by 2.
Yes, sir.
Now I will imagine d like before to be much larger than L. If d is much larger than L, then do you realize L square plus d square will be roughly equal to d square? Agar d square L square se bahut large hai, so this will be roughly equal to d square.
Yes, sir.
Yes, sir.
So then d at P is like mu naught by 4 pi into magnetic moment m divided by this will be d square roughly square root लिया तो d and d cubed हो गया. If d is much larger than this is on the perpendicular bisector of the magnet, right? And
Yes,
is
sir.
the magnetic moment of the magnet. And in a very general sense. Can I wipe this off?
Yes, sir.
Just like we had in electrostats. This is nothing new actually. Exactly the same kind of formulations. Suppose I had a magnet like this. ये तो end-on position or perpendicular bisected position में आ गया. Suppose this was my magnet. South pole, north pole. This is minus n. This is plus n. In general, suppose so. This is a small magnet. 2n. If I had to find at a point P, this point, any point P can be designated by two things, R and theta. R obviously is much larger than L. At this point P, the magnetic field, देखो उन दो positions में the magnetic field was either parallel to M or anti-parallel to M. अब क्या हो जाएगा ना? The magnetic field at P, because we have looked at two cases. That was theta equal to 0 and that was theta equal to 90 degrees. We have looked at two cases.
Yes, sir.
Yes.
And now जब P था, theta was 0, R was D. When the P was here on the perpendicular bisector, theta was 90 degrees, R was D, right?
Yes, sir.
Yes, sir.
In a more general sense, at this point, the magnetic field will have a radial component, BR, and will have a tangential component, B. The magnetic field at P will have a radial component. This is a radial component towards R. And the net magnetic field will be the resultant of these two. And we'll make an angle phi with this. We'll make an angle phi with this. अब हम खाली result बता देते हैं. BR, the radial component of the magnetic field, and of course, like I said, BP will be root BR squared plus B theta squared. Root BR squared BP would be this, and BR, let me tell you, is like mu K की जगह mu naught by 4 pi. 2p था उसमें, twice the
2kp cos theta.
2p था ना, अब इसमें 2m आ जाएगा.
Yes, sir.
2 times magnetic moment. Again, m क्या हो जाएगा? M हो जाएगा small m into 2l magnetic moment. P की जगह 2m and cos theta by r cube. Exactly same kind of result है. देख लो. Radial component of the magnetic field. M is the magnetic moment. And B theta. K की जगह mu naught by 4 pi आ जाएगा. M sin theta by r cube. M is the magnetic moment. Small m into 2l. B theta. इसमें ना, the earlier two results can be obtained from this one result by putting in theta equal to 0 and theta equal to 90. इस position पे था तो theta equal to 0, तो B theta component 0 हो गया. It was just a radial component BR going this way, 2m by r cube. R की जगह D हो जाएगा. उस
Yes.
position में क्या था? Theta equal to 90 degrees. So ये 0 हो जाएगा and we'll have mu naught by 4 pi m by r cube. इसी से आ जाएगा वो दोनों results. यहाँ पे होगा तो theta will become pi.
हाँ सर.
Yes,
Will
sir.
become pi, तो BR नेगेटिव हो जाएगा, ये 0 हो जाएगा. BR नेगेटिव मतलब इस डायरेक्शन में हो जाएगा BR. Got me?
Yes, sir.
Yes,
Yes,
sir.
sir.
That you have to remember. Can I back this off? Let me know.
Yes, sir.
Yes, sir.
Yes, sir.
अच्छा, और एक चीज है. How do you find phi? The angle that the resultant magnetic field makes, tan phi. देखो, tan of this angle will be B theta, which is this.
By BR.
BR. B theta by BR क्या हो जाता है? This by this. देखो, सब कट जाएगा. ये tan theta by 2 आ जाता है. Half of tan theta. The angle that it makes with the radial direction, phi, is given by tan phi is half tan theta. Tan phi is half tan theta, is what you get out of this.
Yes, sir.
Got me?
Yes, sir.
Yes, sir.
Can I back this up?
Yes, sir.
Yes, sir.
All good?
Yes, sir.
Yes,
sir.
sir.
Also, I'm sure by this time you would realize a current carrying circular loop also behaves like a magnet. With magnetic moment, I, number of turns n into the current I that it carries into the area of this, right? A is the area of this.
Yes, sir.
One thing, if you have a circular loop, then where is the north pole and the south pole in a circular loop? Suppose current is like this. एक circular loop को ऐसे देख रहे हो and current is anti-clockwise. देख रहे हो कोई सर? So this end of the loop will behave like one of the poles of the magnet. वो कैसे निकालोगे जानते हो? This will behave, अगर इस तरफ है ना, तो I ऐसा है तो magnetic field ऐसा रहेगा, तो north से तो बाहर आएगा ना magnetic field.
हाँ, sir.
See, north ये इसलिए ये north pole होना चाहिए. अगर उस तरफ से देखोगे, same loop को you see from the other side, you'll find current clockwise इसके पीछे से go behind this loop and see this loop. I hope you understand. If you go behind this loop, then current will be clockwise, है ना? Yes or no?
Yes, sir.
Current clockwise है. Then this end. इसमें magnetic field कैसा होगा? Going into
Yes, sir.
कहाँ से होगा? अगर ये साउथ पोल होगा तो ये साउथ पोल होगा, ये साउथ पोल होगा. So every current carrying loop behaves like a bar magnet. And the end of the loop where the current is going anti-clockwise, that behaves like a north pole. Where the current is going clockwise, that behaves like a south pole of the magnet.
Yes, sir.
And the magnetic moment is NI. All right.
Yes, sir.
Yes, sir.
Now, just give me 2-3 minutes. I'll give my throat some rest. Also drink some water. Just give me 2-3 minutes. 2-3 minutes के लिए pause कर. If there is a magnet, south pole, north pole, length 2L. So obviously, you know, it has a magnetic moment M from the south pole to the north pole. This is pole strength minus M. This is pole strength plus M. Then its magnetic moment is given by what? M into 2L. M into the length. Pole strength into the length, right? And it's from the south to the north. Now suppose the whole thing is placed in a uniform magnetic field B. It's placed in a uniform magnetic field B at an angle theta. Magnet with the axis of the magnet making an angle theta with the axis. So obviously, देखो, this fellow will experience a force like this, M into B. B is the force per unit pole strength. So pole strength M, like this unit, right? This guy will experience, the south pole will experience a force opposite to the magnetic field, M into B, right? So do you realize these two forces are equal and opposite, and they would want to rotate this?
Yes, sir.
These two forces, MP and MB, would produce a torque like this, would rotate this, and
Yes, sir.
form a couple. ये angle theta है, तो ये length देखो 2L sin theta होगा,
हाँ, sir.
होगा ना, ये 2L है तो ये 2L sin theta होगा. The couple produce restoring torque or couple restoring torque produced tau is of magnitude in this case clockwise. इस केस में clockwise produce हो रहा है, ये MP ऐसे rotate करेगा इसको. Clockwise in this case, anti-clockwise भी होगा कभी-कभी. Clockwise is MB, magnitude of either of the two forces, into the separation between these two parallel forces, 2L sin theta. Right? M is the pole strength. But M into 2L क्या हो जाएगा? The magnetic moment vector है.
Sir.
Right? So MB sin theta, M is the pole strength, ये तो pole strength है. But this is capital M is the magnetic moment. Which means now you could have written ये M का ये direction है, B का ये direction है. So MB sin theta, M and B have an angle theta, so I can say the tau vector is actually M cross B. Because the magnitude of torque would be M into B into sin theta, M into B into sine of the angle included, and see M cross B is in this case M ऐसा है, B ऐसा है. So M cross B is clockwise. So ये clockwise ये होना चाहिए था, so clockwise. So torque experienced is magnetic moment cross magnetic field in a uniform magnetic field.
Yes,
Yes,
sir.
sir.
Yes, sir.
Restoring torque. अब ये क्या होगा ना? If This is the direction of the magnetic field. If the magnetic moment is in this direction, if the magnetic moment is parallel to B, in this case, angle between M and B is 0, theta is 0.
Yes, sir.
If the magnetic moment is parallel to B, अब क्या करोगे ना? If you displace it slightly, it would want to get restored to this. This
Yes,
position, it will be in equilibrium. क्यों? Both translational and rotational. MB ऐसे act कर रहा है और ये MB ऐसे act कर रहा है. So obviously, net force is 0. इस case में also net force is 0. This case में net torque is also 0 because the separation between MB and this MB is 0. So torque acting on is 0 because theta is 0, right?
Yes, sir.
Yes, sir.
This position of the magnet is called stable equilibrium. Theta equal to 0, angle between magnetic moment and B is 0. Then that's equilibrium and also stable equilibrium. इसको थोड़ा सा यहाँ से सरकाओगे ना, tilt करोगे तो it would want to come back. It will want to get aligned to B. M would, right? Magnetic moment would want to get aligned to B. ये stable equilibrium होगा. अगर ऐसा होता, this is south, this is the north, then the magnetic moment will be like this, and say magnetic field is like this. In case it is pi, this also is equilibrium in the sense this N will experience a force MB like this in the direction of the magnetic field. This will experience a force opposite to the magnetic field. यहाँ पे भी equilibrium है, but this equilibrium, check for yourself, is unstable equilibrium.
Unstable equilibrium.
Theta equal to pi में unstable equilibrium आ जाएगा. Theta equal to 0 में stable equilibrium आएगा. Got me? Also,
Yes.
let me tell you, without deriving, let me not get into that. But the potential energy of this configuration in the magnetic field is minus magnetic moment dot B. जैसे P dot E होता था, यहाँ पे M dot B होगा, minus M dot B. Potential. Potential energy least कब होता है? Stable equilibrium में.
Maximum unstable.
So which is like, which is essentially like minus M into B into cos theta. M dot B is angle between M and B theta minus M into B into cos theta. Stable equilibrium में potential energy is least. और जब थीटा पाई हो जाएगा ना तो ये प्लस हो जाएगा, पोटेंशियल एनर्जी मैक्सिमम. अनस्टेबल इक्विलिब्रियम में पोटेंशियल एनर्जी लार्ज हो जाएगा, इसीलिए अनस्टेबल है. नेचर को पसंद ही नहीं है ज्यादा पोटेंशियल एनर्जी. नेचर डजंट एंजॉय टू मच ऑफ पोटेंशियल एनर्जी. देयरफॉर large potential energy is an unstable state for mechanical systems. They would rather reside in the ground state where they feel very comfortable with things. Stable equilibrium is a comfortable state and is lowest potential energy. Stable equilibrium is always lowest potential energy. Unstable equilibrium is always largest potential energy, right?
Yes.
Yes, sir.
Yes, sir.
However, ये least or largest, now they are local maxima and local minima in the potential energy graph. They are local maxima and local minima in the graph. मतलब compared to the neighborhood, ना least or maximum है ये. That has to be remembered. Potential energy element. This is also a result to be remembered, minus mb cos theta minus m dot b etc. ms from south to north. अच्छा, magnetic moment क्या होता है? Will be always in the direction of the magnetic field, है ना? अगर कोई in general for magnetic systems. Now, see if this is a material, right?
Yes, sir.
Some crystal exposed to an external magnetic field. exposed to an external magnetic field V naught. Then we define intensity of magnetizing field. The vector H as the vector B naught by mu naught. Intensity of the magnetizing field H. The magnetic field divided by mu naught is defined as the intensity of the magnetizing field. Is defined as the intensity of the magnetizing field. That means the external electric field V naught is mu naught times H. Scalar notation में V naught will become mu naught H. अगर vector notation हटा H is the intensity of the magnetizing field, and it's related to the external magnetic field with a factor mu naught. That's one thing that I want you to know. Sometimes this H is also called the magnetizing force. हालांकि ये force नहीं है, पर इसको ऐसे बोलते हैं, right? It's so H is related to the external electric field V naught. Now, when you subject it to an external electric field V naught, there is a magnetic field which is produced inside the material. There is a magnetic field which is induced in the material. There is magnetic field which is also produced or induced inside the material. What happens is, that means now the atoms will get reoriented and there would be what is called the magnetic, there is a magnetic moment produced inside the material. There is a magnetic moment produced inside the material. If M is the magnitude of the magnetic moment produced, inside the material, because of V naught over a volume V, then intensity of magnetization. So this will give me H is a measure of the field that is trying to magnetize this material. H is a measure of the field that is trying to magnetize this material. But there is some magnetization produced in this material because of V naught.
Yes, sir.
Yes, sir.
Yes, sir.
Is designated by, then we define. अब वो magnetization is produced होगा ना because of V naught. So there will be magnetic moment produced inside the atoms.
Yes, sir.
Right? Then we define intensity of magnetization. Then we define intensity of magnetization. मतलब कितना magnetization produce हुआ? I as the magnetic moment produced per unit volume. Magnetic moment produced per unit volume. V is the volume of this material. Per unit volume.
सर वो नीचे का दिख नहीं रहा सर.
अच्छा ठीक है, रुको हम ऊपर लिखते हैं. एक बार तुम यहाँ से हम बता रहे लिखो. Then we define intensity of magnetization. रुक जाओ, इसको थोड़ा नीचे करने का कोशिश करते हैं.
हाँ सर.
सर
ठीक है सर.
ठीक है बच्चे?
हाँ सर.
Then we define intensity of magnetization I as magnetic moment produced per unit volume because of V naught. ये अंदर ना magnetic moments produce हो जाएगा, मतलब material magnetize हो जाएगा. That will be measured by I. H measures क्या? The magnetizing field. Intensity of magnetizing field V naught by mu naught. आई क्या मेजर करता है, कितना मैग्नेटाइजेशन प्रोड्यूस हुआ, मैग्नेटिक मोमेंट पर यूनिट वॉल्यूम। अच्छा इसमें ना कैपिटल एम इज पोल स्ट्रेंथ इनटू द लेंथ divided by volume. A volume by length will be the area of cross section of the material.
Yes, sir.
This is also
Yes, sir.
pole strength per unit area. This is also pole strength per unit cross sectional area. Pole strength per unit cross sectional area.
Yes, sir.
We can show that the induced magnetic field. So I is the intensity of magnetization. I is the
Intensity.
intensity of magnetization. I is the intensity of magnetization. मतलब अंदर कितना magnetization produce हुआ वो I से measure होता है. Now, if PM is the magnetic field induced, अंदर जो magnetic field induce हुआ इसके कारण because of external electric field, PM is induced magnetic field. Then we can show, I'm not getting into too much of derivations. We can show that BM induced magnetic field will depend on I, will be like mu naught times I. Induced magnetic field will be like mu naught times intensity of magnetization. Induced magnetic field will be like mu naught times intensity of magnetization.
Yes, sir.
Yes, sir.
Total field produced inside the material. B अंदर क्या होगा, कोई भी पॉइंट, एक B नॉट होगा और एक BM होगा.
Yes, sir.
जब इंड्यूस्ड है B नॉट एक्सटर्नल है, BM प्लस B नॉट.
Yes, sir.
BM क्या है, mu naught times I. I is the intensity of magnetization
Yes, sir.
plus B naught is mu naught H. B naught is mu naught H. H is this magnetizing field, intensity of magnetizing field. So mu naught H, right?
Yes, sir.
Yes, sir.
If mu is the permeability of the medium, then mu by mu naught is mu r, relative permeability. Right?
Yes,
Yes,
sir.
sir.
Mu by mu naught is relative permeability. अब देखिए आप, we define another quantity. Can I write this off?
Yes, sir.
Yes, sir.
अब देखो क्या हो रहा है, what is happening. If I expose a material to an external electric field B naught and the magnetization induced is BM. BM is the intensity of the magnetization. अब actually क्या है, B naught is producing intensity of magnetizing H.
Yes, sir.
BM, there is an intensity of magnetization. This is intensity of magnetizing field. This is intensity of magnetizing field, and this is intensity of magnetization.
Yes, sir.
Yes, sir.
We define a quantity called CHI. We call it shy. Don't feel very shy. which is called the susceptibility of the material. As intensity of magnetization divided by intensity of the magnetizing field. ये intensity of magnetization किस extent तक material magnetize हुआ और कौन किया? H per unit intensity of magnetizing field. This was called susceptibility of the material. Susceptibility, magnetic susceptibility. It's called magnetic susceptibility. We can show from this B is the net magnetic field. So I'll have to use the net permeability of the material into H. B naught is mu naught H. Air में क्या हो रहा है, right? पर उस मीडियम में क्या हो रहा है? मीडियम के लिए mu naught की जगह mu, H की जगह H यूज करेंगे.
Yes, sir.
Mu H is mu naught I plus mu naught H. Then what I do is I divide by mu naught into H. I divide by mu naught into H. So mu by mu naught is I by H plus 1. Mu by mu naught is I by H plus 1. But mu by mu naught is relative permeability. And this is 1 plus and this is psi, magnetic susceptibility. Psi is very clearly dimensionless. I and H are same dimension. So this is clearly dimensionless. Clearly dimensionless. So if you know psi for a material, then mu r is 1 plus, relative permeability is 1 plus.
Yes, sir.
Yes, sir.
Yes, one. See again,
Yes,
this
sir.
ऐसे लिख सकते हो. I is like जो हमने क्या Bm by mu naught. I is like Bm by mu naught,
Yes, sir.
right? And H is what? B naught by mu naught.
Yes, sir.
Is susceptibility है. So Bm, magnitude of induced magnetic field, is like B naught into psi. Bm is proportional to B naught. Bm is proportional to B naught. And the factors that separate, see, induced magnetic field is proportional to the externally applied magnetic field,
Yes.
separated by a factor which is magnetic susceptibility. Right?
Yes, sir.
Yes, sir.
Can I write this off?
Yes, sir.
Yes, sir.
2 minute और वेट करेंगे यार, गला इतना स्ट्रेन हो गया है सवेरे से. I'll still give me 2 more minutes. I'll start after 2 minutes. Essentially, when a material is subject to an external magnetic field, different materials will respond differently in terms of getting magnetized. This is an important. So mostly they will ask you theoretical questions on this, but understand this very simple concept. In terms of magnetization, there are 3 kinds of classification. So one, materials in which atoms have paired electrons. I hope all of you understand this, paired electrons.
Yes, sir.
जैसे कॉपर में होता है, paired electrons. Now, if you look at an atom of such a material, तो एक पेयर ऑफ इलेक्ट्रॉन्स को देखो. See, these electrons have orbital motion. These electrons have orbital motion and also spin, right?
Yes, sir.
So each of these electrons are responsible for creating a current
Yes, sir.
Yes, sir.
opposite to electronic current. Each of them can create a current and can create a magnetic moment
Yes, sir.
Yes, sir.
in the direction of the magnetic field that they produce.
Yes, sir.
Yes, sir.
A pair though. Look at a pair of electrons in an atom. One pair. In that pair, let's say one ends up creating a current like this, and the other electron ends up creating an equivalent current like this. They spin in opposite directions, right? In a pair.
Yes,
in an
sir.
atom,
Yes, sir.
right? A
Yes,
pair
sir.
of electrons, right? Now, very clearly, in this atom, is the magnetic moment into the plane of the board?
हाँ, sir.
Yes, sir.
Come out of the plane of. So the net magnetic moment is 0 for this pair.
Yes,
sir.
Yes, sir.
For the pair, net magnetic moment is 0. Is 0. Right?
Yes, sir.
Yes, sir.
Every atom, since it's paired, will produce no net magnetic moment,
Yes, sir.
Yes, sir.
which means if we take a piece of such material, each atom produces no magnetic moment because of the pairing of electrons. Okay?
हाँ, sir.
Each atom will produce no magnetic moment because of this pairing,
Yes, sir.
right?
Yes, sir.
Now, so ये actually पास है ऐसे है, सोचो इसके ऊपर एक बार अलग-अलग ऐसे दिखा रहे हैं, right?
Yes, sir.
Same shell में है तो in a pair, you know, you'll have the same radius, so तो सब same है. I hope all of you understand all of it.
Yes.
Yes, sir.
अब देखो, suppose, so इसका magnetic moment is out of the plane of the board.
Yes, sir.
इसका magnetic moment is
Yeah.
the plane of the board, right?
Yes, sir.
Yes, sir.
Now suppose I apply a magnetic field V naught coming out of the plane. Suppose we apply a magnetic field B coming out of the plane. अब क्या होगा? What will happen is this, because of the magnetic field out of the plane of the board, this guy, which has a magnetic moment like this, इसका जो flux coming out है ना वो बढ़ जाएगा.
हाँ, sir.
तो ये क्या करेगा ना, ये करंट रिड्यूस करेगा ताकि फ्लक्स, इंक्रीज फ्लक्स को कम करने, लेंज़स लॉ होता है उसको, पता नहीं 9-10 में पढ़ाई की
नहीं पढ़ा है, सर.
हाँ, तो ये फ्लक्स नेचर कोशिश करेगा ना कि कोई भी क्लोज लूप से फ्लक्स अपोज करेगा, चेंज ऑफ फ्लक्स अपोज करेगा. फ्लक्स
Yes,
इज मैग्नेटिक फ्लक्स. तो अब क्या करें, इसके कारण भी मैग्नेटिक मोमेंट है यहाँ पे और एक्सटर्नल इलेक्ट्रिक मैग्नेटिक फील्ड भी ऐसा है. तो ये क्या करेगा ना, ये आई रिड्यूस करने का कोशिश करेगा.
Yes, sir.
This
Yes.
electron will slow down. This electron will slow down. तभी तो I reduce हो जाएगा ना.
Yes.
हाँ,
Yes, sir.
sir.
So let me call this 2. So 1. Electron in 2 will slow down.
So flux वाला एक बार.
क्या होगा ना बेटा, ज्यादा मैग्नेटिक फ्लक्स यहाँ से पास करेगा. अब उसको
Yes,
कम
sir.
करना है, कैसे
Yes,
कम कर
sir.
सकते हो?
करंट रिड्यूस कर
करंट
दो।
आई कम करोगे तो यहाँ पे जो मैग्नेटिक फील्ड है वो कम जाएगा,
हाँ सर।
इसका खुद का जो मैग्नेटिक फ्लक्स है वो कम जाएगा,
हाँ सर।
तो असेंशियली वो अपोज कर रहा है,
यस सर।
ठीक है। तो दिस विल स्लो डाउन,
यस सर।
तो इसका मैग्नेटिक मोमेंट डिक्रीज कर गया।
हाँ सर।
स्लो
Yes,
डाउन
sir.
किया मतलब इसका मैग्नेटिक मोमेंट डिक्रीज किया, इसका खुद का मैग्नेटिक फील्ड डिक्रीज किया
हाँ सर।
इन द डायरेक्शन ऑफ बी नॉट, राइट। इसका क्या करेगा, अब ये है ना, ये यहां पे अगर तुम दोगे ना मैग्नेटिक फील्ड, एक्सटर्नल मैग्नेटिक फील्ड, इसका तो मैग्नेटिक फील्ड अंदर जा रहा है,
यस सर।
अब ये
Yes, sir.
बाहर वाला मैग्नेटिक फील्ड को अपोज करने के लिए ना ये अपना अंदर वाला मैग्नेटिक फील्ड बढ़ाने का कोशिश करेगा।
यस सर।
Yes, sir.
और अंदर मैग्नेटिक फील्ड कब बढ़ेगा, जब आई बढ़ जाएगा,
हाँ सर।
तो दिस विल, वो आई कब बढ़ेगा, व्हेन दिस इलेक्ट्रॉन स्पीड्स अप,
यस सर।
Yes, sir.
दिस इलेक्ट्रॉन विल स्पीड अप। तो अब क्या होगा, देखो इसका मैग्नेटिक फील्ड इस डायरेक्शन में कम हुआ, पहले नेट मैग्नेटिक फील्ड जीरो था जब कोई एक्सटर्नल, ठीक है। अब क्या हो गया, इसका एक्सटर्नल फील्ड अंदर का विल बी मोर देन इसका एक्सटर्नल फील्ड बाहर का,
यस सर।
Yes,
तो
sir.
इन दोनों के कारण ना नेट मैग्नेटिक फील्ड बिकॉज ऑफ दीस टू अंदर की तरफ गया, इनिशियली जीरो था बिकॉज यू नो they were paired and they were producing, now after an external magnetic field is applied together they produce a magnetic field, induced magnetic field opposing B naught, together 1 and 2 will produce a magnetic field opposing B naught,
यस सर।
Yes, sir.
1 and 2 will produce a magnetic field opposing B naught. ठीक है, मतलब क्या होगा, दिस इज व्हाट विल हैपन। सो आई हैव एक्सप्लेन टू यू एटॉमिक लेवल पे क्या हो रहा है, इस तरीके जहां पे पेयर्ड इलेक्ट्रॉन्स है, हाँ
Yes, sir.
यहाँ पे पेयर्ड इलेक्ट्रॉन्स है, कैन आई राइट दिस ऑफ,
Yes, sir. Yes, sir.
so if there is a piece of matter like this, यहाँ पे पेयर्ड इलेक्ट्रॉन्स है, and I apply an external magnetic field B naught to this, then what happens is the induced magnetic field will oppose B naught. Bm is going to oppose B naught because एक इलेक्ट्रॉन स्पीड अप हो गया, एक स्लो डाउन हो गया, the net field now they produce induced would be opposing B naught,
यस सर।
ठीक है, this is induced magnetic field. इसका मतलब क्या हुआ यार, ये एक्सटर्नल, सपोज ये बी नॉट कहां से प्रोड्यूस करोगे, ये इस तरीके का बड़ा सा मैग्नेट लोगे तो ये बी नॉट आएगा ना,
हाँ सर।
अब ये बी एम ऐसा है, इसके कारण जो मैग्नेटिक फील्ड इंड्यूस्ड है ऐसा है, मतलब ये है ना नॉर्थ पोल की तरह बिहेव कर रहा है,
यस
हाँ,
सर।
sir.
Yes, sir.
तो इसको रिपेल करेगा,
यस सर।
Yes, sir.
so two things will happen, two things will happen, one, magnitude of bm will be small, induced magnetic field is small, of the order of 10 to power minus 5 SI units to bm, induced magnetic field bm is small, and bm opposes b naught. B naught, this substance will experience feeble repulsion, ठीक है ना, इन दोनों के बीच में रिपल्शन होगा,
यस सर।
राइट?
Yes, sir.
हम लोग ने क्या कहा था, Bm is chi times B naught. अब क्या होगा ना, इसका जो chi है ये छोटा होगा और नेगेटिव होगा, it will be negative. This chi और chi क्या बोलते हैं पता नहीं, is negative for such materials because Bm is in a direction opposite to B naught. So this has to be, so हम लोग ने ये कहा था ना, Bm is chi या chi times B naught. So this chi has to be negative for such materials. Susceptible, magnetic susceptibility is negative. साला मैग्नेटाइजेशन होने की जगह उल्टा ही असर हो रहा है इसका,
हाँ सर,
रिपेल कर रहा है, बदमाश है. नेगेटिव फॉर सच मटेरियल्स, दिस इज मैग्नेटिक ससेप्टिबिलिटी. हाँ, और म्यू आर क्या होता है, म्यू आर इज 1 प्लस chi, which is, अगर ये नेगेटिव है तो दिस विल बी लेस देन 1. म्यू आर रिलेटिव परमिएबिलिटी विल बी less than 1 for such materials.
Yes, sir. Yes, sir.
They will experience repulsion in a magnetic field. Well, the induced magnetic field will be opposite to the direction of the applied magnetic field.
Yes, sir.
yes sir,
Such materials are called diamagnetic materials. Such materials are called diamagnetic materials. Such materials are called diamagnetic materials. इसमें तो नेट मैग्नेटिक फील्ड अंदर B नॉट से कम होगा.
हाँ, sir.
हाँ सर,
Net magnetic field will be B naught minus Bm. The net magnetic field. तो कम हो जाएगा मैग्नेटिक फील्ड अंदर, B नॉट से कम होगा, right?
yes sir,
Yes, sir.
Such
Yes, sir.
materials exhibit what we call diamagnetism. Diamagnetism. This is called diamagnetism. ये किन मटेरियल में होगा? Where atoms have paired electrons. Where atoms have paired electrons, such are diamagnetic. इनका magnetic susceptibility is negative. इनका induced magnetic field will oppose applied external magnetic field. You know what I'm saying?
Yes, sir.
Yes, sir. Yes, sir.
Diamagnetic material है, suppose diamagnetic material. इसमें suppose ये V नॉट अप्लाई की. Suppose I apply B naught in a diamagnetic material. तो क्या होगा? ये अंदर मैग्नेटिक फील्ड B naught से कम होगा, तो सेपरेशन बढ़ जाएगा. These magnetic lines of force will repel each other. ये ऐसा हो जाएगा. है ना, ये सेपरेशन बढ़ जाएगा so that the magnetic field is less than B naught.
Yes, sir.
I hope you realize
Yes, sir.
these magnetic lines of force are repelling each other, so that
Yes,
density
sir.
of lines of force will decrease and will become less than B naught. ठीक है?
Yes, sir.
What happens in diamagnetic materials? Okay, that's one kind of.
yes sir,
There is copper, I remember, is one. You can look up for more diamagnetic materials. दो चार ना important exam के point of view से ध्यान रखना, हमको नहीं ध्यान में. But you guys need to just look up 5-6 materials, common materials.
Okay, sir.
Now, there are some materials electrons are unpaired, paired नहीं in an atom. तो unpaired electron in an atom में, so that will have a net non-zero magnetic moment, क्योंकि उसको cancel
Okay.
करने वाला कोई है नहीं. There is no one that
Okay.
can cancel that magnetic moment. So every atom has a magnetic moment, right?
Yes, sir.
yes sir,
Every atom, therefore, has an unbalanced, non-zero magnetic moment. Even before a field is applied, her atom will have a magnetic moment. But the point is, what happens is, but these magnetic moments in a piece of matter are random. मतलब एक piece of matter लो. I'm not applying the external electric field. This is before applying the external electric field. ठीक है? ऐसा किसी एटम का मैग्नेटिक मोमेंट ऐसा है, किसी का ऐसा है, किसी का ऐसा है, किसी का ऐसा है, रैंडम है, ऐसा है, किसी का ऐसा है, रैंडम है. This is the direction of magnetic moment, randomness. And large sample size, randomness produces no bias. That means the net magnetic moment will be zero. Because they are random, and so although every atom, ये एक atom है जिसका magnetic moment है because of an unpaired electron. ये एक atom है जिसका magnetic moment is direction है because of that unpaired electron. Every atom will produce a unbalanced magnetic moment, but together is piece of matter का. And so the net of these magnetic moments, इसका magnetic moment इसका zero हो जाएगा. In a piece of such matter. So net magnetic, every atom has a non-zero magnetic moment, but together in the net magnetic moment zero hai, before an external electric field is applied. Magnetic field is applied, right?
Yes.
Now,
Yes, sir.
can I wipe some of this?
Yes, sir.
Yes, sir.
Have you finished copying this?
Yes, sir.
Yes, sir.
Yes, sir.
Now, यही इसी मटेरियल का बात कर रहे हैं अभी. I'm talking the same material. Now, when a B0 is an external B0 is applied, there is slight alignment of these magnetic moments. मतलब क्या होगा? Then a B0 I apply like this. Then this will थोड़ा सा, there will be a weak alignment. There will be a weak alignment in the direction of B0. Some of them will kind of get aligned. There is a weak alignment. There is a weak alignment. Nevertheless, there is still some alignment. So there is a net magnetic field induced inside the material. There is a weak, which is like a weak induced magnetic field in the direction of B0. बहुत ज्यादा नहीं. ये this BM will be weak. There will be not complete alignment. There will be partial alignment. So there will be some BM magnetic field induced in the direction of B0. And now, ऐसे को अगर if you place it, यहाँ पे नॉर्थ पोल इसका है, अब इसका नॉर्थ पोल यहाँ है, इसका साउथ पोल यहाँ है, right? So it will experience attraction. It will experience attraction. If BM and B0 are in the same direction, there will be attraction.
Yes, sir.
Yes, sir.
There'll be attraction. Now, Bm, for such material, Bm is B0, right? This chi is the magnetic susceptibility. This time, since Bm and B0 are in the same direction, this will be positive, but small. Unpaired electron है यहाँ पे. Every atom has an unpaired electron. That's why this happens. But it weakly, when an external magnetic field is applied, it weakly aligns. So that induced magnetic field is small.
Yes, sir.
So this will be small. This magnetic susceptibility for such material will be small. Not only that, if we reduce B0, if we remove B0, ये साला वापस पगला की तरह अपना ओरिजिनल रैंडम पोजीशन में आ जाएगा. Bm vanishes once again. मतलब magnetism is lost. Bm is a measure of magnetization produced. So in such cases, अगर B0 को हटा दोगे तो Bm खत्म हो जाएगा. ये वापस जो इसका atoms है, they will get into random positions.
Yes, sir.
Yes, sir.
Such materials are called
Paramagnetic.
paramagnetic. पढ़ लियो सर.
नहीं सर, केमिस्ट्री में भी पढ़े थे, जिस पर डिजाइन कुछ पता नहीं था सर.
को केमिस्ट्री में पढ़े हो ये सब? तो हमारे
Solid
में
state,
टेस्ट
sir.
करवाए हैं.
सर रीजन विजन कुछ पता नहीं है सर, बस इतना पता है कि अनपेयर्ड होगा तो पैरामैग्नेटिक होगा.
अच्छा. तो ये इसका मैग्नेटिक ससेप्टिबिलिटी पॉजिटिव रहता है, पर बहुत छोटा वैल्यू रहता है, ऑफ द ऑर्डर ऑफ 10⁻⁻⁵ वगैरह.
Yes, sir.
Yes, sir.
अच्छा. और इसमें B0 को हटा दोगे तो वापस डीमैग्नेटाइज हो जाएगा ये मटेरियल, Bm 0 हो जाएगा, राइट?
हाँ सर.
दैट्स अ सेकंड काइंड ऑफ मटेरियल. तीसरा, सो दिस इज पैरामैग्नेटिक. पहला क्या था? डायमैग्नेटिक पेयर्ड इलेक्ट्रॉन्स. दूसरा क्या था? अनपेयर्ड इलेक्ट्रॉन्स. पैरामैग्नेटिक. आई थिंक चेक कर लेना बेटा, आई एम श्योर नहीं. आई थिंक एल्यूमिनियम इज पैरामैग्नेटिक. सो दिस इज पैरामैग्नेटिक. एक बार चेक कर लेना. आई थिंक एल्यूमिनियम इज पैरामैग्नेटिक.
Yes, sir.
अच्छा. Third kind of material, last for the day. ये जो थर्ड काइंड है ना, इसमें भी also has unpaired electrons. But this material has a special property. So क्या होता है इस मटेरियल का, जो हम जिसका बात करने जा रहे हैं, मैं आपको इसमें ना एक पीस है, यहाँ पे एक डोमेन है, यहाँ पे ऑल एटम्स हैव मैग्नेटिक मोमेंट इन द सेम डायरेक्शन. फिर एक डोमेन है जिसमें ऑल एटम्स हैव मैग्नेटिक मोमेंट इन द सेम डायरेक्शन. फिर एक रीजन है इसमें where all atoms have the same direction of magnetic moment. Then again there is a region where all atoms have the same direction. So it's broken down into this thing. बड़ा peculiar है ये मैटर. All atoms, this entire piece of matter is broken down into what we call clusters. These are called clusters. ये cluster है, ये cluster है, ये cluster है, cluster है, cluster है, cluster है, ऐसे बहुत सारे clusters में broken. And the point is, in every given cluster, magnetic moment of atoms will be in the same direction, but different from another cluster.
Yes, sir.
Yes.
And what happens here? This, of course, it's a little more difficult phenomenon to understand why they are clustered. This is actually because of, अभी बताना मुश्किल है थोड़ा, because of quantum mechanical effect. I can't explain it to you at this level. It's because of what is called quantum mechanical effect. These clusters are formed. अब क्या होगा बेटा? Now, if we apply B naught to such a material, so now all of these get clusters will align in the same direction. All of these clusters will perfectly align in the same direction. All clusters will get aligned in the same direction. All clusters will align along B naught. All clusters will align along B naught, and a large BM is induced in the direction of B naught. In the direction of B naught, a large magnetic field is induced. So BM is this times B naught. So इस material में क्या है? This is large and positive. This magnetic susceptibility is large and positive. This chi is large and positive in such a material. Large extent of magnetization.
Yes, sir.
And such materials are called ferromagnetic materials. Ferromagnetic materials. Of course, iron है, nickel है, cobalt है, और भी है. अब इसमें एक फंडा है. This chi is large and positive, but what happens is, beta, if I heat this material then ये alignment उतना नहीं होता है. The magnetic susceptibility will decrease. On heating the material, magnetic susceptibility will decrease. An induced magnetic field will decrease. अब क्या होगा ना? There is a certain temperature. उसके ऊपर अगर heat करोगे ना, so it will no longer have this property. This, first of all, this will get converted into paramagnetic material. This will get converted into a paramagnetic material above a certain temperature. This will get converted into a paramagnetic material above a certain temperature. वो clusters का सब बराबर हो जाएगा, खून खराबा हो जाएगा clusters का. If I raise it above a certain temperature, and the temperature above which such materials get converted into paramagnetic materials is called the Curie temperature. P is Curie temperature. I think for iron, the Curie temperature is 740 या 770 डिग्री सेंटीग्रेड ऐसा कुछ है. If you raise iron above 770 degree, it will no longer be ferromagnetic. It will become paramagnetic. ठीक है?
Yes, sir.
Yes, sir.
Yes, sir.
अब देखो, I have tried to cover a few things in that chapter, magnetism and materials. In 20 years, I have never taught this chapter because it always takes a toll on the throat. 20 साल में हम पहली बार ये chapter पढ़ा है, okay? Because it's always extremely boring to teach this chapter. But you know, I thought, let me finish it this time. There might be small little pieces that I might have skipped, but read it from a text. By this time, you would have got an overall view of this. Books will do a very bad job in explaining to you terrestrial magnetism. Book से पढ़ के ना terrestrial magnetism समझना मुश्किल है, उल्टा पुल्टा बोलते हैं सारे, क्योंकि मैथ्स तो पता नहीं है उनको. मैग्नेटिक मेरिडियन कैसा प्लेन होता है, कहां से वो प्लेन डेट, किसी फिजिक्स वाले को नहीं पता. ठीक से मैथ्स उन लोग को आता ही नहीं है, तो ना बुक्स बहुत गंदा जॉब करते हैं ट्राइंग टू एक्सप्लेन terrestrial magnetism. I would have liked to teach you more terrestrial magnetism, but I thought it was not necessary to go beyond what I taught. This was enough. But I'm done with this chapter. We can move to electromagnetic induction. After there are small, you still have to read the textbook because I might have missed out small little things here and there. Okay. So mostly I would have done everything. Small little things could be left out. So you can just read through the chapter. By and large, we are through with chapter 2 on this magnetism and matter. I can now cruise on to chapter 3. इसमें छोटा examples, board level, mains level, ना direct formula based आता है. Angle of depth, tan delta BV by BH, etc. वो छोटा alpha वगैरह, small little things will come. You should understand. I've tried to explain to you the concept. I don't want to spend time solving problems on this because they're very simple problems, which you can do all by yourself. Just go through some examples of a textbook. That will be enough.
Okay, sir.
It's easy, though boring. Nevertheless, we are through with this. I think we can now do things that are not boring. This much for today. We'll see you tomorrow.
Sir, कल